In the case of a function f in two constraints, say g equals k and h equals c, we have that del f is equal to lambda del g plus mu del h, a linear combination of the gradients of the constraints. That is to say, del f is in the plane determined by del g and del h. With that in mind, we're going to find the extreme values of f of x, y, z equals z, subject to x squared plus y squared equals z squared, and x plus y plus z equals 24 simultaneously. As before, we need our gradient vectors. Del f is equal to 0, 0, 1, excuse me there. Del g we'll say g is related to the second equation, and del g is going to be 2x, 2y, negative 2z, imagining that we've gotten everything on one side set it equal to 0. Del h is equal to 1, 1, 1. Our gradient equation is going to be del f is equal to lambda del g plus mu del h. So equation 1 is going to be 0 is equal to 2 lambda x plus mu. Equation 2 is 0 is equal to 2 lambda y plus mu. Equation 3 is 1 equals negative 2 lambda z plus mu. Notice now, though, we have x, y, z, lambda, and mu. We need 5 equations, so we bring in both constraint equations. So the fourth one is x squared plus y squared is equal to z squared, and the fifth one is x plus y plus z is equal to 24. If we think a bit, we might realize that we can subtract equation 2 from equation 1. If we do, we're going to get that x is equal to y. Now, we're going to find a clever way to use this. Trying to use equation 3 with either equation 2 or 1 is not going to work out so well, because we have this term that's 1, and we aren't going to end up getting rid of both lambda and mu. It'll be kind of a mess. You can give it a shot. I'm suggesting that we have these two equations, 4 and 5, that have x, y, and z in both of them. If we replace x by y, or y by x, in these two equations, we're going to end up with a system of two equations and two variables. So that's the path I'd like to take. If I let x equal y in equation 5, then we get that 2x plus z is equal to 24, or that z is equal to 24 minus 2x. If I then put x equals y and z equals 24 minus 2x, both of them, into equation 4, then we get 2x squared is equal to the quantity of 24 minus 2x squared. In this last equation, we can FOIL and end up with pretty big numbers in a kind of a terrible quadratic equation, or just square root both sides. Plus or minus the square root of 2 times x is equal to 24 minus 2x. Combining like terms and then factoring out x and dividing is going to give us x is equal to 24 divided by 2 plus or minus the square root of 2, which we can split up into 24 over 2 plus the square root of 2, and then 24 over 2 minus the square root of 2. And if we do this and then rationalize the denominators, and then simplify the results, we're going to get that x is equal to 24 plus or minus 12 times the square root of 2. Now earlier in our journey we saw that x was equal to y, but let's go back and see what we're trying to find. We want the extreme values of f of x, y, z equals z. Folks, we just want the extreme value of z, or values. z is equal to 24 minus 2x. We know what x is. Let's find what z is. If z is equal to 24 minus 2x, then z is equal to 24 minus 2 times the quantity of 24 plus 12 times the square root of 2, or z is equal to 24 minus 2 times the quantity of 24 minus 12 times the square root of 2. By simplifying these expressions, we're going to find that the maximum is negative 24 times the quantity of 1 minus the square root of 2, and the minimum is negative 24 times the quantity of 1 plus the square root of 2.